Hey guys, welcome to Unit 6.3, where we're going to talk about another factor that affects pressure, temperature. All right, but let's begin by reviewing some of the things we've done in 6.1 and 6.2. So let's do our questions of the day. If you like, you can pause now and give these a quick try, and then you can restart up. Don't forget, as we're going through this, at any point I'm going too fast, remember you are allowed to pause me. All right, so let's look at conversions. In Unit 6.1, we talked about going from one pressure to another. All right, so I need to stop sharing. All right, so remember we have our basic standard pressure, right? 1 atmosphere equals 760 mmHg, which equals 101.325 kilopascals. All right, so we're going to convert here. We're going from mmHg to atmospheres. So remember, I'm always going to put what I start with up here. What I want to go to up here. And remember, what's up here has to be down here. So I'm going to plug in these two. 1 atmosphere, 760 mmHg. And I'm going to divide these two. I'm going to take 798 divided by 760, and I get 1.05. All right, so that was from 6.1. Let's look again at what our next question is. All right, so this is a review from Boyle's Law. So remember, Boyle's Law says P1 V1 equals P2 V2. So let's look at our question here, and then we'll plug in where we're going. If 250 milliliters of gas at a pressure of 755 mmHg is compressed to a pressure of 840 mmHg, what is the new volume? All right, so let's fill in what we know. P1, pressure 1 is, so I'm looking for a unit of pressure, mmHg is on there, so that's 755 mmHg. V1 is 250 milliliters. It's going to be compressed to a pressure of 840 mmHg, which is P2, and I'm trying to find V2. V2 is my X. So let's make a quick prediction, right? And then I'll plug it in. We know two pressures. We're going from 755 to 840, so pressure is going up. So what does that mean for volume? It must go down. So let's find out if volume goes down. All right, so here are our variables here, so we're going to plug in. So I'm going to take 755 times 250 equals 840x. So I'm going to multiply 755 times 250, and I get 188,750 equals 840x. Now I want to solve for x, so I'm going to divide by 840. And I get that x is 224.7 milliliters. So yes, pressure went up, volume went down. All right, so that's a little bit of a review from 6.1 and 6.2. So let's get into 6.3. Today we're going to talk about temperature. All right, so we're going to introduce a new unit today called Kelvin. We're going to talk about Kelvin. Kelvin is our standard unit of temperature in chemistry when we're dealing with gas laws. But let's review our previous units of volume. Units of volume, remember, we're looking for milliliters, liters, centimeter cubes, or decimeter cubes are all units of volume. And Units of pressure consists of mmHgs, atmospheres, and kilopascals. All right, so hopefully you're open to your note page 6.3, and we're going to talk about temperature. So what is temperature? Well, temperature is the measure of kinetic energy of molecules. Remember we talked about kinetic energy back in 6.1, energy in motion. So temperature is the measure of how rapidly the particles are moving. And what we find is temperature is directly proportional to Ke. So in this case, temperature goes up when kinetic energy goes up. So if the particles move faster, temperature goes up. So temperature is simply a measurement of the average heat or energy of the particles in a substance. So how fast are those particles moving tells us that. And it's directly proportional. If particles move faster, temperature goes up. So we just talked about that. As temperature increases, particles move faster. There's more kinetic energy. So this is a directly proportional relationship that we are talking about here. All right, so in the metrics, we use the Celsius scale quite a bit. And just so you know, we've talked about Celsius before. The freezing point of water in Celsius is 0 degrees Celsius, and boiling point of water is 100 degrees Celsius. I know that we've used the thermometers before and have tried to get our water as close as possible to boiling with 100 degrees Celsius there. However, when we're dealing with gas laws, we're going to use what's called the absolute temperature scale. And this is referred to as the Kelvin scale. And what we know is that volume becomes 0, meaning the absence of movement, the absence of volume becomes 0. There's nothing there when temperature reaches negative 273 degrees Celsius. So this is extremely cold. They are not moving anymore. Those particles are done, right? And so we call this absolute 0. And the reason it's referred to as the Kelvin scale is because it was found by a gentleman named Lord Kelvin. And as you guys know, in science, we love naming things after the people who discover them. So absolute 0 on the Kelvin scale is negative 273 degrees Celsius, which is really cool. Remember, 0 degrees Celsius to us is like 32 degrees. So going way down, we're talking extremely cold. So why we use this scale is because we never have to deal with negatives. That's the really nice thing here, is that all of our temperatures will be positive. So we're never going to have to worry about negative numbers, which is really awesome when we're doing our math here. So what we know is, look, it's another conversion factor. 0 Kelvin equals negative 270 degrees Celsius. So this one's a pretty easy one to convert. So if we're going to go from a Kelvin temperature back to Celsius, we simply subtract 273 from that number. If we want to go from Celsius to Kelvin, we're going to add 273. And guys, from here on out, when we're using any type of temperature, you have to turn it into Kelvin. You're going to see that I'm going to give you problems that have Celsius in them. You need to turn them to Kelvin. So I've mentioned to you guys before standard pressure. Well, we actually refer to something called STP, which is standard temperature and pressure. Okay, so remember, standard pressure was 1 atmosphere, or it was 760 mmHg, or 101.325 kilopascals. Well, standard temperature and pressure will be 273 Kelvin and 1 atmosphere. So this will be, if you see things that says this gas is at STP, you know that that gas is at 273 Kelvin and at 1 atmosphere. All right, so let's go ahead and look at, on 6.3, let's practice some converting to Kelvin degrees, okay? So we're gonna stop sharing here. So if you look at the end of your notes, we have 23 Celsius to Kelvin. All right, so remember to convert to Kelvin, so degrees Celsius to Kelvin, the rule is we add 273. All right, so we have 23 degrees Celsius. What is that in Kelvin? Well, I'm going to take 23 plus 273, and I get 296 Kelvin. All right, now I have a negative 11 degrees Celsius. What's that in Kelvin? Well, I'm just going to take negative 11 plus 273, and I get 262. And then I have what says 32 degrees Fahrenheit. You're like, what's that? Well, remember, we just talked about that. That's freezing. So at freezing, that equals 0 degrees Celsius. So in Kelvin, 0 plus 273 be 273 Kelvin. So pretty easy. If you're going from Celsius to Kelvin, simply add 273. All right, let's look the opposite way. What if I'm going to go from Kelvin to Celsius? In this case, I subtract 273. Okay? So the first one says 315 Kelvin. How many Celsius? So I'm going to take 315 and minus 273 from it. And I get 42. All right, then I have 277K equals how many degrees Celsius? So I'm going to take 277 minus 273, and I get 4 degrees Celsius. This last one says 212 degrees Fahrenheit. Well, into just Celsius. Well, 212 Fahrenheit is boiling point. So if you refer back, that is 100 degrees Celsius. All right, so your assignments to work on. Here in a minute, I'm going to go through practice 6.3 with you, and we'll do a few examples, and then you'll need to finish that. And then we have our temperature ed puzzle. So you'll need to log into Edpuzzle. So the link will take you directly to the site. Go ahead and sign in, and you should see the temperature ed puzzle. I believe it's about 3 or 4 minutes long, and it has about 6 or 7 questions to it. And so you need to watch the video and answer those questions. And the assignment is due for Maroon Day, April 23rd at 11 p.m. and for Gold Day, April 24th at 11 p.m. All right, let's talk about 6.3, practice. For number 1, you are simply doing some converting, just like we just did. You're going to convert from Celsius to Kelvin and from Kelvin to Celsius. So let's look at the first 2. Let's do 1A and 1B. So remember for 1A, it's going from 24 degrees Celsius equals how much Kelvin? All right, so remember when we go from Celsius to Kelvin, we add 273. So we're going to take 24 plus 273, and you're going to get 297 Kelvin. For 1b, we're going to go from Kelvin, 24 Kelvin equals what degrees in Celsius? And in this case, we subtract. So we're going to take 24 minus 273. In this case, you'll get negative 249 degrees Celsius, which would be extremely cold. Now remember, as we move on into Charles' law, which will be unit 6.4, we're going to make sure we're always using Kelvin. So oftentimes I'm going to give you Celsius. You've got to convert it to Kelvin. And remember, that means we're going to add 273. All right, so you need to do 1, C, and D on your own. Number 2 says if energy is applied to a particle, think heat. Heat's a type of energy. Will the particle speed up or slow down? So think about it. We talked about this earlier. If you increase the temperature, what happens to those particles? Number 3 simply asks, how are temperature and kinetic energy related? Think about what's the definition of temperature. So you can go back into your notes and look at that. Number 4 says if the average kinetic energy of nitrogen molecules is increased, meaning we speed up, we increase the movement of those nitrogen molecules, what happens to the temperature? So think about it. What happens when we speed up those molecules? Number 5, if the temperature of a gas decreases, how does that affect the motion of the particles? Is it going to speed them up or slow them down? Number 6, if molecular motion stops, period, what do we call that on the Kelvin scale? When all motion stops, there's no more volume, they are not moving, it's extremely cold, that is referred to as what unit? We talked about that earlier too. All right, then number 7, what is the boiling point of water in Kelvin? Let's do that one together real quick. So 7, boiling water. Do I know what the temperature of boiling water is in Celsius? Yeah, it's 100 degrees Celsius. And I want to turn that into Kelvin. So what do I need to do? Add 273. So I'm going to take 100 plus 273, and I'm going to get 373 Kelvin. So I did number 7 for you there. 8 lists the 3 states of matter. And then number 9, in which state of matter would the particles have the greatest motion? So of the 3 states of matter, here I'll go ahead and give you number 8 too. Solid, liquid, gas. I know you already knew that, you didn't need me to tell you. Which one of those do the particles move the fastest? And in which one does it move the slowest? We talked about that back in 6.1. All right, guys, so please finish 6.3 practice and then work on your Ed puzzle. Hope you guys are having a great week. I'll see you soon.